This is just an extra video, and I thought I would just do some examples of taking limits of different sequences for you. So maybe some of the techniques we've been talking about in parts 1 and part 2 you'll be able to bring some of those ideas together. So I'm just taking these problems out of a different book, and the first one will be n cubed over n to the fourth plus 1. Something I haven't talked about in class, and I think is the best way to take these types of limits, is to just look at the term that is growing the fast and divide it, the numerator and denominator, by that term. In this case, of course, n to the fourth. So we don't change it, we're just changing the way it looks. Dividing by n to the fourth on top, we have 1 over n, and on the bottom we have 1 plus 1 over n to the fourth. And now you look at the parts that 1 over n goes to 0 as n goes to infinity. 1 over n to the fourth goes to 0 as n goes to infinity. So we can see that this goes to 0 over 1, which is 0. The limit is 0. Now this same technique could be used in this problem. 3 to the n plus 1 plus 3 over 3 to the n. Now there's other ways to do this. You could create an inequality and use our little theorem about r to the x. But let's just look at the most powerful term growing the fastest in the numerator and denominator, and it is 3 to the n plus 1. So I'm going to say this is equal to 1 plus 3 over 3 to the n plus 1 over 3 to the n over 3 to the n plus 1. Well, let me write it. 3 to the n over 3 to the n plus 1. That's equal to 1 plus 1 over 3 to the n, canceling out factors of 3, and on the bottom I have 1/3. So look, this is very easy. Once you do this, you can see which parts of this go to 0. 1 over 3 to the n goes to 0, and our limit then is 1 over 1/3, which is 3. The limit is 3. Let's do another example using the same technique. Number 3. Let's do n over e to the n plus 3n. Well, you know this is going to go to 0 because the bottom has e to the n in it. But here's a way that you can, if we restrict ourselves to saying if the bottom blows up and the top goes to a constant, that's when we can say the limit is 0. Then we would divide by the most powerful term that we see, the one that's growing the fastest. So we would have n over e to the n over 1 plus 3n over e to the n. Now we know that the exponential beats out n. Actually, you could use L'Hopital's once on this, but you don't need to. We know that that goes to 0, and likewise this. So our quotient goes to 0 over 1, or 0. And one more example using the same kind of technique. K over the square root of 9k squared plus 1. Well, here I would write this as the square root of, and I'd put everything under the same radical. K is equal to the square root of k squared, so this is k squared over 9k squared plus 1. Now we can just look at what happens in here and take the square root of that limit. So, well, I guess I'll do it. You can see what the limit is. but the most powerful term in this quotient, growing the fastest, is the k-squared terms. So we'll divide by k-squared. We don't care about the constant 9. So we have k-squared over k-squared is 1, and 9k squared over k squared is 9, plus 1 over k-squared. Well, now we can see clearly this goes to 0, and so our answer is arrow, taking the limit, the square root of 1/9, or 1/3. The answer. Here's an example where we could use the squeeze theorem. Minus 1 to the n times n over n plus 1. Well, we know that this satisfies the following inequality. Minus n over n plus 1 is less than or equal to, let's call that thing a sub n, is less than or equal to n over n plus 1. So now I can look at each of these, and I know if I divide by n on the top and bottom here, I'd have minus 1 over 1 plus 1 over n, less than or equal to a sub n, less than or equal to, dividing by the most powerful thing in the numerator and denominator, 1 over 1 plus 1 over n. Now we know that 1 over n goes to 0, and so we have this quotient goes to minus 1, and this one has a limit of 1. Well, that sure didn't do me any good, did it? I wasn't thinking, and I don't want to do this whole thing over. Nothing's wrong here, but I realize that I'm making a mistake. So who cares if a sub n is between minus 1 and 1? That doesn't give us anything. This sequence will not converge because you have minus 1 to the n times n over n plus 1. This goes to 1, but it's toggling back and forth between numbers very close to 1 and minus 1. And so this does not have a limit. We'll write the limit as n goes to infinity of this does not exist. Sorry about that. Sometimes, you're just not thinking, you don't think of the right path to go on right away. And the minute I saw minus 1 to the n, I was thinking, oh, we'll put it in between two bounds and use the squeeze theorem. Well, so I did put it in between two bounds, but they were minus 1 and 1, which didn't do me any good, but it alerted me right away to the fact that I had neglected to see n over n plus 1 just goes to 1, not 0. So anyway, I think sometimes you benefit from seeing that it's common for all of us to start off on a path and realize that it's not going to take us where we want to go, so we redirect our attention. Okay, so here's another example, and I see that the argument of these log functions are becoming infinite, and so is this. So what we have here, if I tried to take the limit right away, I see this is infinity, and this goes to infinity, and infinity minus infinity is an indeterminate form. We cannot evaluate the limit this way, so we try to rewrite this. Remember that the natural log of a over b is equal to natural log a minus natural log b. So we can use that property of logarithms to rewrite this expression. We have natural log a minus natural log b, so I will write it as the natural log of n cubed plus 1 over 3n cubed plus 10n. Well, now I can look at the inside here and see what happens to this argument of the logarithm. And if you divide by n cubed everywhere, the most powerful, fastest growing term, n cubed, we haven't changed anything, and this would be equal to the natural log of 1 plus 1 over n cubed over 3 plus 10 over n squared. So now you can look at that and see that this goes to 0, 10 over n squared goes to 0 as n goes to infinity, and so we see the answer to our question. The limit, now notice I'm not writing LIM everywhere. So when I write these equal signs, I mean it is equal. Now I'm taking the limit as n goes to infinity. Instead of writing out all the limit notation, I write arrow. And I mean as n goes to infinity, this limit is the natural log of 1/3. Now here's an example where we have n both in the base and in the exponent. And I can't take limits that way. If I tried, I would say, well, the base becomes infinite, and the top is going to 0, and infinity to the 0 is another indeterminate form. So I have to change the way this looks. So I'm going to use the fact that e to the natural log of this, n to the 2 over n, would be equal to n to the 2 over n. And so what I'm going to do is I am going to try to take the limit of this, the exponent on e. Why do I want a log in there? Well, it's so I can get that 2 to the n down by using the natural log. Let me write the natural log of a to the n is equal to n natural log a. So I'm going to use that when I take the limit of this exponent. Alright, so now I take natural log of n to the 2 over n, and I write this as 2 over n times the natural log of n. Now, if I just tried to take the limit here, I would get 2 over n goes to 0, natural log n goes to infinity. 0 times infinity is an indeterminate form. But I can rewrite this as we have done. I can write this as 2 times natural log n over n. Now I have infinity over infinity, and I can use L'Hopital's rule. So I'm going to draw a little arrow, and I'll put LR. If I was really being careful, I would put this now in terms of x, because you can't take derivatives when n is just has integral values. But we'll just go ahead and write 2 times 1 over n over 1, which is equal to 2 over n, which has a limit of 0. So the exponent up here, this exponent, goes to 0. So our n to the 2 over n will go to e to the 0, or 1. N to the 2 over n, the limit as n goes to infinity, is equal to 1. Another example, 1 over n to the 1 over n. Well, I think I would write this as 1 over n to the 1 over n. And we have already seen that this goes to 1, so the whole thing will become 1. Let's do one more example. The natural log of 1 over n over n. Well, the first thing you always do is see, when you have a quotient like this, you try to see what's the limit of the numerator and what's the limit of the denominator. well, the denominator goes to infinity, and 1 over n goes to 0 through positive values, so the natural log is going to minus infinity. Always have the little graph of natural log in your mind, not in your calculator. There's the natural log, and as its argument goes towards 0 through positive values, we see that the function is becoming negative without bound. So we have minus infinity over infinity, and this will allow us to use L'Hopital's rule. So I'll put arrow with LR here, and then let's take the derivative of the top and the derivative of the bottom, remembering that we are doing it with natural log 1 over x and x, but I won't change the notation. So let's see, the natural log of 1 over x, if we're going to take that derivative, we would have 1 over n, which is n, times the derivative of 1 over n, which is minus 1 over n squared. So that was what we'd have on the top. And on the bottom, the derivative of n is 1, or x. And so this is equal to minus n over n squared minus 1 over n, and the limit is 0. Is that kind of a surprise to you? We have a quotient where the numerator is becoming negative without bound, the denominator is becoming positive without bound, and yet the quotient is becoming arbitrarily close to 0 by just going far enough out in the sequence. So I've got more room here. I'll do one more example. You guys don't really have to watch this, but I suggest that you try each of these examples and make sure that you can do them. The last one, e to the minus n over 2 times the sine of e to the minus n. Now I would get rid of the minus 1 factor in the exponent and write this as 1 over e to the n over 2 times the sine of 1 over e to the n. Now I can look more carefully and see what's happening. The whole numerator is going to 0 because we have constant on the top, the bottom is blowing up. Now here the argument of sine is going to 0, and as think of the graph of sine. The argument is going to 0 through positive values, so we see that the sine of that is also going to 0. So our whole denominator is going to 0. 0 over 0 is an indeterminate form, and it allows us to use L'Hopital's rule. So let's see. We want to take the derivative of e to the minus n, which will be minus e to the minus n, over, and now we want to take the derivative of the denominator, which will be, using the chain rule, 2 times the cosine of 1 over e to the n times the derivative of 1 over e to the n, which is, well, I'll put it in parentheses, minus e to the minus n. Oh boy, these cancel. That's nice. So we have this is equal to, simplifying, we have 1 over 2 times the cosine of 1 over e to the n. Now I look at that argument, the argument of the cosine, and it is going to 0. The cosine of 0 is 1, and so the limit is arrow 1/2. Now, if you want to check, sometimes just take a big value of n. Once you do something like this, take like n equals 100 and put it into your calculator and see if you get something close to 1/2. But don't try to take your limits that way. You have to show what you are using. If it's L'Hopital's rule, the squeeze theorem, if you're dividing by the most powerful thing in the top and the bottom, you need to show by your work exactly what technique you're using for taking the limit.